Have you ever wondered what lies beneath the surface of powerful data analysis? How do computers sift through massive data sets with such incredible speed? Often the answer is a library called NumPy. Think of it as the silent, powerful engine in the world of data science in Python. It's the foundational layer that many other famous tools are built upon. Pyramid diagram showing NumPy at the base with other libraries above Pandas matplotlib. Without NumPy, the entire ecosystem would move much slower. It's like trying to build a skyscraper without a solid steel frame. The structure simply wouldn't hold up under the immense weight and complexity of modern data. So why should you care about this hidden engine? Because understanding NumPy is like learning the fundamental physics of data manipulation. It gives you direct control over how numbers are stored and processed. This isn't just an abstract academic exercise. It translates into writing code that is not only faster, but also cleaner and more intuitive. When you work with large collections of numbers, stock prices, temperature readings, pixel values in an image, you need a tool that is designed for exactly that purpose. Regular Python is fantastic, but it wasn't built for high-performance numerical computing. NumPy fills that gap, and it does so beautifully and efficiently. Imagine you're an artist. Python gives you a wonderful set of general-purpose tools: brushes, canvases, a rainbow of paints. But what if your art involves creating intricate mosaics with thousands of tiny tiles? You'd want a specialized tool, something that lets you handle all those tiles at once, arrange them and change their colors collectively. NumPy is that specialized tool for the data artist. It lets you work with entire collections of numbers, what we call arrays, as single cohesive units. This shift in perspective, from handling one number at a time to manipulating whole grids of them, is the secret to its power. At first glance, a NumPy array might look a lot like a standard Python list. You can store a sequence of numbers in both. But underneath the surface, they are fundamentally different creatures, designed for entirely different purposes. A Python list is a marvel of flexibility. It can hold anything: an integer, a string, another list, a function, you name it. This flexibility, however, comes at a cost. Each item in a list is a full-fledged Python object, with its own type information and metadata. This means the items can be scattered around memory, linked by pointers. It's like a messy bookshelf where each book is a different size and shape. A NumPy array, on the other hand, is all about order and efficiency. It's a grid of values, and every value must be the same data type. All integers, all floating point numbers. This constraint is its superpower. Because elements are uniform, NumPy stores them in one continuous block of memory. Think of it as a perfectly organized bookshelf with identical books. When you grab a book, you know exactly where it is and how big it is. This compact storage is the first key to NumPy's incredible speed. Now that we understand why NumPy arrays are so special, let's get our hands dirty and create some. The most common way to make an array is by starting with a Python list. To do this, we first need to import the NumPy library. By convention, the community imports it as NP. So the first line will almost always be import NumPy as NP. This alias saves you from typing NumPy repeatedly. It's a small tradition that signals you're part of the club. Let's start with the simplest case, a one-dimensional array. Imagine a list of daily temperatures for a week: 72, 74, 78, 80, 79, 75, 73. Pass the list to np.array. To convert it, code temperatures =, np.array, 72, 74, 78, 80, 79, 75, 73. And that's it. Your first NumPy array. It may not look like much, but you've organized that data into a highly efficient structure ready for fast computations. This is the fundamental building block for almost everything we'll do. Of course, data rarely comes in a single neat line. We often work with tables or grids. This is where multi-dimensional arrays come into play. Let's say we have sales data for 2 products over 3 days. We could represent this as a list of lists in Python, 10, 12, 15, 8, 9, 11. The first inner list represents product A. The second inner list represents product B. We can convert this into a 2-dimensional NumPy array with the exact same function. Code, sales_data equals sign np.array, 10, 12, 15, 8, 9, 11. Now we have a 2x3 grid NumPy can handle easily. Beyond converting lists, NumPy provides convenient functions for creating arrays from scratch. Need an array of 10 zeros? np.zeros, 10. Need a 3x4 matrix of ones? np.ones, 3, 4. Need numbers 0 through 9? np.arrange, 10. Arrange acts like Python's range but returns a NumPy array. These helper functions save you from typing large lists by hand. They are the scaffolding for your data structures. Once you have your data neatly packed into NumPy arrays, the real fun begins. This is where you start to see the elegance and power of the library. Performing mathematical operations on these arrays is incredibly intuitive. Unlike with Python lists, you don't need to write for loops to iterate through the elements one by one. Instead, you can apply operations to entire arrays at once. This concept is called element-wise operations, and it's a cornerstone of working with NumPy. It makes your code not only dramatically faster, but also much easier to read and write. Let's imagine we have 2 arrays of the same size representing the prices of items at 2 different stores. Store 1 underscore prices equals sign np.array 1.00, 2.50, 3.00. Store 2 underscore prices equals sign np.array 1.10, 2.40, 3.00. If we wanted to find the price difference for each item, we could simply subtract one array from the other. NumPy automatically understands that you want to subtract the first element of store 2 underscore prices from the first element of store 1 underscore prices, the second from the second, and so on. The result is a new array, -0.10, 0.10, 0.00. It's that simple. This same principle applies to all the standard arithmetic operations. You can add multiply divide quantities equal sign np.array 10, 5, 8. Prices equal sign np.array 2.0, 10.0, 5.0. To calculate the total revenue for each product, you can just multiply the 2 arrays together. Revenues equals sign quantities prices. No loops, no complex syntax, just clean, readable math. This element-wise approach is what makes NumPy feel so natural for anyone with a background in mathematics or science. It lets you think about your data in terms of vectors and matrices, not just disconnected lists of numbers. You can also perform operations between an array and a single number, a concept we'll explore more deeply when we discuss broadcasting. For example, if you wanted to apply a 10% discount to all prices in an array, you could simply write discounted underscore prices equals sign prices 0.9. NumPy is smart enough to multiply every single element in the prices array by 0.9. This simplicity frees you to focus on the logic of your analysis rather than the mechanics of looping. Creating and manipulating whole arrays is powerful, but often you need to access or modify specific parts of your data. This is where indexing and slicing come in. Just like with Python lists, you can access individual elements of a NumPy array using square brackets. For a one-dimensional array, it works exactly as you'd expect. If you have an array, for example, temperatures equal sign npeeps array 72, 74, 78, 80, then temperatures 0 will give you the first element, 72, and temperatures 2 will give you the third element, 78. This is your most basic tool for pinpointing a single piece of data within your collection. For multi-dimensional arrays, the concept is similar. but you use a comma to separate the indices for each dimension. Think of it like coordinates on a map. The first number is the row and the second is the column. If you want to get the value from the first row and third column, which is 15, you would write sales data 02. The row index comes first, then the column index. This row-column syntax is a clean and unambiguous way to navigate your grid of data, allowing you to select any individual cell with precision. Slicing is the next step up, allowing you to select entire subsections of an array. It uses a colon syntax, start to stop, to grab a range of elements. If you wanted to get the first 3 temperatures from our temperatures array, you could write temperatures 03, 72, 74, 78. The real power of slicing shines with multi-dimensional arrays. Want to select the entire first row of our sales data array? You can use sales data 0. The colon in the column position acts as a wildcard, meaning give me all the columns. Similarly, sales underscore data 1 would select the entire second column, giving you 12 and 9. What's truly powerful is that you can use indexing and slicing not just to select data, but also to modify it. If you discover an error in your sales data, say the first day's sales for the second product should have been 7, not 8, you can directly change it. Sales data 10 equals sign 7. You can even change entire slices at once. If you wanted to update all of the first product sales to 0, you could write sales data 0 equals sign 0. This ability to precisely target and modify parts of your array is essential for data cleaning and preparation, a critical step in any data science workflow. It gives you surgical control over your data set. As you work with data, you'll find it doesn't always come in the shape you need. You might have a long, one-dimensional list of sensor readings that you want to group by day or by hour. This is where reshaping comes in. Reshaping changes an array's dimensions without modifying the underlying data. Imagine a long string of beads rearranged into a rectangular grid. The beads stay the same and remain in order, only the layout changes. It's a common, powerful operation in data prep. Imagine a one-dimensional array of 12 numbers, perhaps monthly sales. Monthly underscore sales equals sign np.arrange 12. That gives you values 0 through 11. Want to view this quarterly? Reshape into a 2-dimensional array with 4 rows, quarters, and 3 columns, months per quarter. Command, quarterly underscore sales, equal sign monthly, underscore sales dot reshape, 4, 3. Rule, element count must stay the same. 4 times 3 equals 12. Valid. Reshape is flexible. You could make it 3 by 4, or 2 by 6, or 6 by 2. NumPy also allows a lazy dimension. Want 3 columns but not the row count? Use -1 as a placeholder. Example, monthly underscore sales dot reshape -1 3. NumPy figures the rows. It will pick 4 rows for 12 elements. Handy when array sizes may change. A common use is machine learning with images. A grayscale image is a 2D array of pixels. A 28 by 28 image is a 28 x 28 NumPy array. Many ML models need a flat feature vector per sample, so unroll the 28 x 28 grid into a 784 element vector 2828 equals sign 784. You can do image.reshape 784 or simply image.flatten. Reshaping bridges your data to what analysis tools require. We've seen how NumPy performs operations on arrays of the same size. But what happens when you try to perform an operation between arrays of different sizes? For instance, add a single number to every element in an array, or add a one-dimensional array to a two-dimensional array. This is where broadcasting comes into play. Broadcasting describes rules NumPy uses to handle arrays with different shapes. It's essentially stretching the smaller array to match the larger shape. Simple example, prices equal sign np.array, 10, 20, 30. You want to add a flat shipping fee of 5 to each price. In NumPy, you write price is plus 5. Behind the scenes, NumPy treats 5 as a scalar and broadcasts it to 555. Then it adds element-wise to give 15, 25, 35.